Welcome back. So a media website believes the average daily visits are 100. Mu equals 100. The population standard deviation of daily visits is known to be 10. So sigma is 10. After an advertising campaign, they suspect daily traffic is now above 100. They randomly sample 30 days of visit counts at alpha equals 0.05 or 5%, test if the true mean is greater than 100. In other words, has the advertising campaign worked? So let's take the average of from their sample. It's 105.83, and the population hypothesized historic was 100. So the question is this difference a real difference or just the result of sampling error? So let's finish this off. So the sample size is 30. We are actually given sigma, or the population mean, in the problem. That's 10. And alpha, 5%. Expected variability is going to be the same that we've been using. And the raw critical value is going to be measured as a particular value for x bar. It's a z-score. And we are after the probability of x bar. So the distribution here is normal, mu 0. We're up here going for a critical value. Now, this is a directional test. We only have one line. Which direction? They suspect they're above. Above means to the right. So it's going to be a right test. It's not going to be that big. We'll make it smaller in a second. Hypothesized mean from the problem is 100. Expected variability is going to be population standard deviation divided by the square root of the sample size. And then our probability now is all on one side, so we don't divide by 2. And then we take, now this is all to the right, so over here we do norm.s.inverse of 1 minus the probability of x. And then our x bar is going to be the z-score times the standard error plus the population mean. So our critical value cutoff is a 103. Down to the test statistic, same distribution, same direction of shading, but it's not going to be that big. Hypothesized mean is still equal to that 100. Variability is still this guy. And the raw sample mean given in the problem is that one. The test stat from that is going to be equal to that number minus the hypothesized mean divided by standard error. Oops, I did it wrong. Let's see, y x bar minus mu divided by the expected. Oh, I think I have an extra equal sign in there. That's why. There. And the probability of that number, it's to the right. So this is x bar to p of x bar, and we're looking to the right. So it's 1 minus norm.s.dist. So 1 minus, I'm going to start out with an equal sign, or it's going to be mad at me. Equals 1. No, I really messed up. Oh my gosh. Equals 1 minus norm.s dist z true. So really low probability. So, and it's way out here, so it's definitely statistically significant. Now it's not kind of sitting in the right spot, so you can, when that happens, you can drag it back to where it should be. Okay, so statistically significant, looking good. Our null hypothesis is going to be that they're equal. And now this is directional. So the direction is that we're to the right or we're greater than for the alternative. The standard error is calculated the same way. It's a z-score. And our test statistic is to the right of the critical value, so it's higher than the large critical value. And our p-value of that's 0.1%, so that's less than 5%. So we need to say that too. Less than alpha. And the conclusion is that we're going to reject H0. We think it's more than sampling error, and we think that we're bigger. All right, now let's go for the margin of error, which, as we mentioned before, there's your formula, norm dot equals norm dot S done inverse. Of 1 minus O. Now, it's alpha divided by 2. And again, it seems odd, right, that it's still alpha divided by 2, even though it's just one direction. But it is. That's the way this one's calculated. Oh, and it's then times the standard error. So times the standard error. There we go. All right, and then to get the lower, you start out with the sample mean minus the margin of error. And then you have the sample mean plus the margin of error. So we're saying that the true population mean from which this sample came is not the hypothesized population mean, but it's somewhere in this green area between 102 and 109. You know, round numbers. All right, while we're up here, let's go ahead and do Cohen's d to see if, so we know we're significant. Let's see if the effect size is big. So that is equal to x bar, which is this one, minus mu, divided by standard deviation. That's 0.58. That's a big number. So it's right here. It's a moderate effect. Signals a significant operational or market advantage. That's good news. So actually, we can actually answer this question already. Statistically significant, moderate effect, and the action would be take action, right? That's awesome. All right. Now, approximately what rho value is a whole number is the upper cutoff. So that's between 102 and 103, 102 and 104, so it's 103. What's the difference between the critical value and the new sample x bar? So from the graph, it's the difference between 106 and 103, so it's 3. Because it's asking for effectively a whole number that's shown on the graph. Obviously, it's a little bit different than that. What are you estimating with the confidence interval? With the confidence interval, we're measuring the true population mean from the sample that we got. And what's the size of one standard error from the graph? That is equal to 2, right? From 100 to 102, so it's 2. And why isn't that right? well, I'll fix it by the time you get to it, because that should be 2. And what is the raw value at 3.2 standard errors? Which is right here. It's 106. And with that fix, you should be all set. We'll see you in the next video.